Today we are going to talk about exponential functions. Now please turn to page 542 and let's look at an example of our exponential function. At the bottom of that page, okay, we have 542. We have this thing right here. Please look at the bottom. And we have two functions here. There's f of x equal 2 to the power x. That is the exponential function. The other one is just 2x. That's the good old nothing function, okay? So as you can see, if x is on top like that, which makes it exponential, and what happens is that your values increase fairly rapidly, especially after a while. Okay, at first things don't look that different, right? 1 and 2 values are the same, but as time goes on, let's turn to the next page. Then the exponential function grows exponentially, which is why people say that. See, 4 by 6 is a lot bigger, and that change increases drastically after that too. Okay, eventually it just the 2 to the power x will leave the power 2 times x in the dust. Seriously, so that would be an exponential function. In general, exponential functions are just functions with x on top, okay, at the exponent position. And let's look at the middle of this page. We're now we're now on page, I can't find the page number. Where is it? 543, the following page. Let's look at the middle of the graph and look at this. What happens when x is negative? Okay, now when x is negative, then as you might remember that to the negative power is the same as 1 over that number. That is 2 to the power negative 3 is 1 over 2 to the power 3, okay, which is 1 over 8. Similarly, 2 to the power minus 2 is 1 over 2 to the power 2, which is 4. In general, the negative exponent just means you have to put it in the denominator and stick 1 over it. Okay, that explains all. That applies for all negative exponents. So and then anything to the power 0 is 1. Okay, and that's a that's a general rule. And remember that when it comes to exponential functions, we don't care about the base being negative. That is, you notice this is the power 2 here. Okay, we're not gonna the number that is in the base of the exponent will always take a positive number, because it just doesn't make sense to take negative numbers in that case. And it gets things complicated because negative number, when it's squared, it becomes positive. When it's cubed, it's negative again. And it just, it just wobbles all over the place and doesn't make any sense. So for exponential functions, the base, which is the number 2 here, okay, for the exponential function, here 2 is called the base, right? And well, it used to be called the base too, I think. Either way, the point is we'll choose the base to be positive so that everything makes better sense. Now, the function that we just mentioned about 2 to the power x, if you have to plot it on the graph, it will look something like this. And then as x is negative, then the function will get closer and closer to 0, but it stays positive. Okay, and then when 2 is bigger, when the x is bigger than 0, then it starts increasing and increases faster and faster, and then start raising to the top, growing exponentially. So then at the bottom of the page, notice that we'll quickly mention that the domain of an exponential function, that is the possible values for x, in this case, f of x equal to 2x. The domain is anything, okay, minus infinity to infinity. The range is always positive, partly because, well, we only use positive numbers as the base. So the range is always on top. You're not going to go to the bottom of the y values. And then as x goes to infinity, then f of x goes to infinity. But when x goes to minus infinity, f of x will go to 0. As you can see, the function just gets closer and closer to the x-axis as x becomes very negative. And that's because it becomes a fraction, okay? Like, for example, x to the minus 3 because 1 becomes 1 over 8. Then x to the minus 4, 2 to the minus 3 is 1 over 8. Then 2 to the minus 4 is 1 over 16. So as you increase the negativeness of x, then the function just gets closer and closer to 0, but it stays positive. So that is the exponential function. And with that information, let's look at example 1, where we consider some on the next page. Okay, on page 544, let's look at example 1, where we only have to figure out which ones are not exponential functions. The first one looks like an exponential function, okay? The second one is not, because the exponential function has to have x on top. This one does not have x on top. That's just your regular cubic function polynomial. This looks like an exponential function. This is not, because the base, which is the thing that's being raised to x, cannot be negative, okay? Otherwise, it doesn't make any sense, because it will be positive sometimes and negative other times, and who knows, and then it won't be defined in other cases. Like when you have the power 1/2, right, which is taking the square root. You cannot take the square root of a minus number unless you introduce complex numbers, which we don't feel like right now. Okay, so that is example 1. So that one is not an exponential function, or at least not allowed to be one. All right, so next let's consider example 2 on page 545. All right, now that problem is quite straightforward. Okay, we need to plug in 2 and figure out what this is. So let's do that. So that is 2 it goes in the position of x. We have 5 times 3 to the power 2 plus 1 is 3, and that equals to 3 to the third power is 3 times 3 times 3, which is 9 times 3 is 27 times 5, so it's 5 times 27, okay? And that is whatever that is. And I'll pull out the calculator after I find it, and then we'll figure out what that is, okay? Yeah. Okay, so I got 135, which is the right answer. So let's look below what and read about what an exponential growth is, okay? Now, a function that models exponential growth is such that is where f of x equal to a times b to the power x. Now, a is the starting value. That is, when x is 0, then b to the 0 is 1, then f equals to a. So a is called the starting value, and b is the growth factor. Well, okay. So having said that, let's look at an example. Let's look at example 3, okay, which is on page 547. So let's read example 3. Now, the population of India is 1.25 billion in the year 2013, okay? And the annual growth rate is 1.2%, all right? So we are going to write it as PT equals to 1.25, that's the initial value, and then 1.012 is the growth rate of 1.2%. And then that's raised to the power t. And t is the number of years since 2013, all right? What will be the population in 2031? Okay, so let's do that. All right, so we have a situation where the 1.012 is the growth rate, okay? The growth rate is 1.2%, so we write it down right here, and that's how you write it. And that's 0.012, and that's the original number, okay? And the total growth rate will be 1.1012. And then to the time is in number of years is the difference between starting at 2013 and get to 2031, which should be 18 years. So if that is, subtract, but after I did some subtraction. So all said and told, we just need to plug in the 18, and that should give us the answer for the population in 2031. Okay, so I have entered into my calculator, as you can see. I have 1.25, okay, times 1.012 raised to the power 18. Okay, so that should be right. Let's check the answer. And the answer is 1.549. Okay, let's see if the book get the same answer. Yes, it does. And therefore, I got it right. All right, so that is that. Now next, let's look at the next example. Example 4 on the bottom of the page. Okay, let's read this thing. In 2006, 80 deer was introduced in some wildlife place, and by 2012, the population will become 180 deer. All right. So, assuming the population grows exponentially, how we need to write some function that represents the deer growth. Okay. So we have we start out with 80 deer. Okay, so well, anyway, so the population formula stays the same. So PT equal to the initial population, which is 80 deer, and then times what's the growth rate? We don't know what it is. Okay, so we'll call it something. Is some unknown number? B. Let's just call it B. Okay, we don't know what the growth rate is, and then how long has it been? 2006 and 2012, so 6 years. So in 6 years, it become 180 deer. 180. 180. All right, so 180 equal to this stuff. Okay, and then with that, we should be able to figure out what the growth. This is the growth rate, and we should be able to figure out what the growth rate is. And to do that, let's solve this equation. First, we need to isolate the b, okay? And so which means we need to get rid of the 80, and that is simple enough. We'll just write down 1/8 divided by 8. I'm ignoring the 0. Now, and then there's b to the power 6 right here, and then right? And then so to find b, then b will be equal to this thing to the 1/6 power. This thing in here is the same as 9/4. We'll calculate the I need to hold my marker just right. Okay, 1/6 power of that thing will be equal to b. Okay, so let's type in the 1/6 power. And notice the reason it's 1/6 powers is because I undid the 6 here, okay, by doing 1/6 on each side, and then we'll turn the 6 into 1, and the other side got a 1/6 on it. Yeah, okay, so let me type this into the calculator. All right, I have to type it into the calculator. Now, the formula doesn't look that hard, right? But you have to be careful that to put in the proper parentheses. First, the 9/4 has to be in parentheses, and then the 1/6 also has to be in parentheses. If you don't, something weird might happen. And so once that's typed in, that should be good. And our answer is 1.14, we'll call it 1.145. Okay, we'll round up the last number. So that equal to, actually, we'll just, let's see if the book agrees with us. I got 1.145, 1.1447. Yep, that is correct. And then what that means, however, is that the growth rate is 1.1447, which means it is, in other words, you can call it 14.47%. Okay, that's where the percent come from. The percent is the number after 1 right here. This is a 1.2%, and our answer is a 14.47% growth rate. Yeah. Anyway, so that's that. And next, let's look at example 5. Now, by the way, be sure to do all these examples that I go over yourself as well. Okay, and well, by not looking at the explanation, and just do it without it, and see if you can come up with the right answer. So so let's look at example 5. Exponential model with where the initial value is not known. Well, whatever. It says find an exponential function that passes through the points -2, 6 and 2, 1. Okay, so we have an exponential function. Let's call it, what do we call it? F. Okay, the book calls it something. We'll call it that too. Okay, we will first, let me write this stuff down. So I have a problem written down. We have some kind of a function, but we don't know either A or B. However, we're giving certain information, like clues. We have minus 2, 6, and 2, 1 as part of the graph. And with that, hopefully we can come up with what the function is. Basically, we need to figure out what A and B are. So, so let's consider the first point, okay? This is, so when x is minus 2, we'll write down AB to the power minus 2. Then f of x equal to 6. Similarly, when x equal to 1, that is AB is equal to 2. Okay, and then so then what happens is then we can play a trick here. So then what happens is let's say b equal, well, it doesn't matter which one you do. Let's call it, let's substitute which one? A. Okay, we'll call A, then from this equation we know A equals to 2 over B, all right? And then we'll plug it in here and see if anything good happens. 2 over, so this is A, all right? I'm writing down A here as 2 over B times B to the minus 2, that's the same as B squared on the bottom, okay? This is the same thing. And then this is equal to 6. So let's solve, this will enable us to solve for B, okay? And then, so then we're gonna do something, well, B is on the bottom here, so let's move B across the equation sign to the top. That becomes B cubed up here, okay? And then move the 6 across the equal sign down to the bottom. That's 2 over 6 equal to 1/3. So then B equals to the cubic root of 1/3. And then A equals to, A then equals to 2 times that thing, 2 over this thing, okay? A is 2 over B. So A is the cubic root of 1/3, and which is equal to 2 times the cubic root of 3. Because to divide by a fraction is to invert and multiply, okay? So that becomes the square cubic root of 3 over 1, and we don't have to worry about the 1. So that would be, this would be the answer. Oh no, I messed up. This says that this is when x is 2, f of x is 1. So there should be AB2 equal to 1. All right, that is, so let me erase the board and try again. All right, let's try again. Okay, now AB x is 2 and f of x is 1, right? Which is f of x is y. So try again. So what is that? Then A equal to 1 over b squared. All right, then we will put that in here the same way, except do it with the right numbers. So we have 1 over b squared times b, this is also 1 over b squared, so we have the total of 1 over b to the power 4, b4, all right, so equal to 6. So so let's move the b up across the equal sign to the top, okay, b4, and then push the 6 across the equal sign down, equals to 1 over 6. So then that gives me b equals to the 4th root of 1 over 6. All right, now let me check. The book agrees with me, so we can move on. Now in the meantime, A is 1 over b squared, which equals to, now b squared is just the square root, okay? That is, the square root of 1 over 6. Which is equal to divide by a fraction is to invert and multiply, which is equal to square root of 6 over square root of 1, and that's just the square root of 6, okay? Because the square root of 1 is also 1. Now let me check again. What is that? That's A. A equal to, what does it say A equal to? Well, whatever. Let's, okay, let's calculate exactly what this is on the calculator, okay? So I will type it in. Now to do the 4th root is the same as doing the 1 over 6 to the power 1 over 4. That is in the definition of things. If you don't remember this in detail, please review chapter 1 where it talks about radicals. Now, so this is the same thing, and that is how I typed it into the calculator. Okay, 1 over 6 to the power 1 over 4, and so that is that. That equals 0.63 whatever. Okay, and then and what does the book say? That, yeah, that looks right. And then I'll also calculate this, what is the value of a, which is just the square root of 6. And well, okay, that now I got this square root of 6 is 2.449, which yep, that is what the book says. And so that is correct. And as a result, the function will be given as the value of 2.449, that's a, all right, and then 0.639 to the power x as written down here, which is those are very neat, clean numbers. I usually deal with, in algebra class we usually deal with cleaner numbers, but but ones with a lot of decimal points are okay too. So that is that. So please do that yourself. And then we'll look at the next thing. And now we have to look at some graph of some function and try to figure out what the exponential, equation is. All right. So let's. This is example 6. On page 550. Now we have a graph, and then so the first thing we'll write down is that the function being exponential has to be y equal to a times b to the power x. Okay, we just need to determine what a and b is. Well, first, when you look at the function, you notice that when x is 0, y equals to 3 right there. Okay, when x is 0, look up there, y is 3. That means a has to be equal to 3. So we know this much, 3b to the power x. All right, and what else do we need? And then when x is 2, okay, look at the graph a little closer. When x is 1, y appears to be x. But to play it safe, let's look a little farther. Because when you're too close to each other, because the first number we considered was 0, if you consider numbers are too close, then you might introduce error. So let's move over a little bit. And x is 2, y appears to be 12. So 212 is a value. So y is 12 when x equal to 2. All right, so that means the base has to be equal to 2, right? Yeah, because 12 divided by 3 is 4. B squared is 4, means B is equal to 2. And well, at least that's a nice number. And we're not going to accept B can also be -2, but we don't accept negative values for the base. Okay, this thing for the base of exponential functions. So the positive one is it. And then, so next, let's look at, we're going to skip example 7 and go, because it tells you how to graph something with a fancy button, but how often do you need to do that? In my experience, I've never done it. Having to graph exponential function and wish that I had a button to push it so that it's faster. Yeah, so let's skip that, okay? And if you need to, you can always do so. But I just don't see where the need is. Anyway, so let's look at the next page. I'm now on page 552, where there is the compound interest formula. The compound interest, yeah, is one big way to use the exponential function. Here's the compound interest formula, okay? The logic behind it, we're not going to think about why this formula works for now, and we're just going to use it and try to calculate various stuff. Okay, so that's the compound interest formula, and the various things have specific meanings. P is the principal, R is the interest rate, And n is R is the interest rate as in per year, and n is how often it's being compounded, like say 12 times a year, then you divide by the 12. So that's what n is, how many times. Else, if you only compound it once a year, then n will be equal to 1. And then t is the time in terms of years. And yeah, so anyway, that is the formula, and we are going to use that formula to calculate compound interest. And the only hard part about using the formula is just remembering which one is what, okay? And basically, just remember n is how many times you're compounding. So let's look at example 8. And it says we are investing $3,000, paying 3% compounded quarterly. Quarterly means 4 times a year, okay? So the n in that formula is 4. And how much will it be in 10 years? So t, the time, equals 10, and n equal to 4. And let's, I will write down that formula. So let's look at the compound interest on page 552. First, here's the formula, okay? And to do this kind of problem, you only do one thing, that is plug in all the appropriate numbers. The principal is $3,000 in our case. 1 plus the interest rate is 3%. Which is translated into 0.03. Okay, that's very important. Now, how frequently it's being compounded is 4 times a year. So you write down the 4 for n, and also write it down up here to follow the formula. And then the amount of time is 10 years. So now that we got all this stuff done, that's it. The next job is let's type this into the calculator and see what comes of it. So I have it typed into the calculator, okay? I have 3,000, okay, times 1 plus 0.03 divided by 4, close parentheses, okay? And then I move over a little bit. Raised to the power 4 times 10, I just typed in 40. If it's a hard number, then you have to put it in parentheses, okay? It depends, I guess. Some calculator might be able to handle it without parentheses, but the safest course is just to put it in parentheses if necessary. But in this case, I just typed in 40, and then and that should do it. And so we will push the answer, and it says $4,045 after 10 years. Is that right? Let me check. Yep, that looks right to me. So that's good. That's example 8. Now please do that yourself as well. And then example 9 on the next following page. Let's look at this. Okay. Then it says something about a 529 plan. Ignore that. The point is, keep reading. Somebody want to set up a account, blah, 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 to grow. Okay, they have $40,000, that's the principal, okay? Invested 18 years, that's the T. And then 6% compounded twice a year. So N is 2, R is 6%. And then, what was it? Oh, the account has to be $40,000. All right, so this is $40,000. We don't know what this is. That's what we're looking for. All right, so let me write that down. Okay, so we want the result, the final amount to be 40,000. Here's the principal, and we don't know how much that should be. So 1 plus 6% interest compounded twice a year. So the 2 is down here and up here, times 18 years. Yep, I think that's right. So I typed that into, so that means what? That means I need to, we need to calculate what P is. So P then equal to 40,000 divided all of the stuff. Okay, so let me write that down. Actually, I don't think I'll write it down. I will just remember that. Okay, imagine this whole thing down here. That will be equal to P. So 40,000 is going to be divided by this whole works. All right. Okay, so I typed it into the calculator. So we have 40,000 divided by everything here after P. Okay, I have here, let's see, 40,000, okay, divided by 1 plus 0.06 divided by 2, that's just 0.03, of course. And raised to the power 2 times 18, I think I wrote down 36. All right, that should do it. And let's see if some reasonable answer come up. Is 13,800. Is that right? Let me check. That is correct. So if you start with $13,800, after 18 years, then your account will be $40,000. All right. So that is example 9. So please do that yourself as well. And now let's look at the bottom of the page where we're going to introduce a number called E. And what's E? E comes from this formula, okay? Now, if you consider this formula right here without the P and the T, so you just have, and let R be just 1 or something. Yeah. So then you have this interesting formula. Okay, I don't know how interesting that is. But anyway, so we have this thing, okay? So consider this specific formula which only has N in it. And then what happens is that if this value starts at being 2, and as you increase the N, okay, this value will approach like an asymptote. It will approach a certain value. It gets closer to and closer to 2.718, etc. And so because usefulness in things like compound interest and stuff, this particular value is given a name. It's like pi, okay? Besides pi, which is 3.14159265, etc. And the E, this number is the other number that also has a name to it. It's not as famous as pi, and it's 2.718 is how we normally memorize it. But we will, it will be called E. Okay, and so the number E means 2.718, and you don't have to remember that. I don't think it's just something you know. Okay, is related. E is related to the compound interest, among other things, and it is the other number besides pi that has a name. All right, so there's this. So now that we have E, and example 10, we will, I don't know what the point of example 10 is, so we'll ignore it. Okay, maybe to show you how to use, let's do example 10, just to show you how to punch E into the calculator. Okay, so please look for E on your calculator, and we'll do this. All right, now I want to show you exactly how to do E. E is usually related to the natural log of the natural log, which is called ln. It might be called ln on your calculator. And I'll wait for the screen to zoom in. Is it going to zoom in? Yeah, there it is. And anyway, well, it's kind of hard to see. Can you see it? I think my hand is making it hard for you to see. Anyways, I'll put it a little closer. Okay, there it is. See, there's a little E there on top of the LN button. That is the E. And oops, it zoomed out again. Anyways, to get the E on my calculator, you will push the Shift button, which is on the other side, this one right here. Okay, I'll see if it'll zoom in again. It's not going to zoom in. Well, anyway, maybe if I pull it out a little bit, you can see better. In any case, the point is there is this E business, okay, and you push Shift LN. Yeah, it's zooming in pretty good. You push Shift LN, and that will produce the E button. And I will show you right now. There it is. Okay, and then the book wants us to do 3.14 for some reason. Fine. Does that ever happen? I don't think so. I don't remember it. And so anyway, that gives us some value, and that is how you punch in E on the calculator. Yeah. Anyway, that's that. So next we have something called look at the bottom of the page. We are now on page 554. Let me write that down. Okay, at the bottom of the page 554, we have another formula. We're not going to go into why the formula works, okay? We're just going to use it, just similar to this one. This is one formula for when you have an interest rate compounded however many times. This is the continuous growth. That means we don't care how many times you compound it. It keeps being compounded all the time, basically. Anyway, so, and the formula looks like this in that case with the E in it, okay? The E is that, E is the number that's in your scientific calculator, or any calculator. It should be, well, most calculators have E in it. When I say most, I mean any calculator in your cell phone, computer, tablet, they will always have a scientific version that you can kick it in. And of course, you can buy a real scientific calculator. They cost about $10. And except for the TI-84 or something, the scientific calculators are not expensive. The graphing calculators are extremely expensive, and I dislike them. Anyway, so anyway, this is the continuous growth or decay formula. Okay, so where we have AT, and we have the E is a number you already know. Okay, so what you don't know here is A and R and T. And with those information, then you can figure out how bacterial growth or something rots and stuff like that. Yeah, so that's that. So let's look at example 11. Okay, example 11, we have calculating continuous growth. All right, so a person invests $1,000 in an account, earning 10% per year compounded continuously. How much was in the account at the end of 1 year? All right, so we're going to, what is this again? Let me write this stuff down. So we will follow the continuous formula that we learned from in the previous page, where AERT, E is a number that's 2.7 something, 728 or something like that, and everything else is the variable. So first we're gonna, A is the starting point, okay, when T equals to 0, that will be A. So, and then the principal is 1,000. So let's write that down. In this situation, we have 1,000, and then continuously growth for 1 year, right? E, and then the rate, what was the rate again? Rate is 10%. Okay, rate is 10.10, which is just 0.1, and then time is 1 year, so that times 1. Okay, I'll write it down here, times 1, which is just 0.10, and that's that. Fairly simple example. So let's type this into the calculator and see what it says. Okay, I have it typed into the calculator as 1,000 times E. Okay, there's the E there. E to the power 0.1. That's the whole problem. All right, so let's see what it says. It becomes $1,105. Is that right? Yep, that is correct. So that is that's that. Okay, and then the next, well, I will finish this video finish this class in the next video.